well, my mass at some point will start to increase, making my acceleration smaller. Which means my change in velocity will get smaller, which means eventually I will just start approaching the speed of light, but never actually get to it. This relationship with how the mass changes, we will get to that as we get through the derivation of E equals mc squared. The math is accessible to you. Questions to hear?
So what kind of energy is that when describing mc squared to potential energy?
It actually, it's not potential. As you pump energy into it, it becomes kinetic energy and rest energy, in essence. You got the 1/2 mv squared. As you get more and more kinetic, as you get closer and closer, m starts to increase, and so your kinetic energy stops increasing because of the change in speed, starts increasing more because of the change in mass. Other questions?
What exactly is going on? Like, why is the mass increasing as the speeding, or like as the acceleration increases?
All of this stems from the assumption, and experiment backs it up. All of it stems from the assumption that the speed of light is constant regardless of the reference frame. And these are just the implications of that one assumption. And then the mathematics, and then you get to the derivation with the mathematics and go, oh, this is what the mathematics claims, let's test the mathematics. And so, I mean, ultimately, why could be considered a religious question, you know? It just seems to be the way the universe works. And I feel like that's an unsatisfactory answer, but that's what I got. There's only so far any science can go in answering why anything happens. Because anytime you have an answer, then the question is, well, why is that true?
So is that movie Interstellar, is it accurate?
I have actually not seen Interstellar. It's been recommended many times to me. Have you seen Princess Bride yet?
Yes, I watched it this weekend.
Okay. How was it?
I get the reference now.
No wonder you're a biochemist. And Jesse, you were the other one. Did you watch it yet?
I was gonna watch it and I was like, princess something, and I just never figured it out.
That's even.
Top 5 movie.
I'll watch it tonight.
Well,
It sounds like it is good. It's a great movie,
I went
despite
on
her
the-
reaction.
I went on the reviews and they were like, if you watch it now, it's not as good as if you watched it before, like 20 years ago or something. So maybe it's the generation gap.
Sure.
Huh.
Yeah.
What's wrong with this generation? Yeah, I understand some things don't a lot of the time. But that one does. All right. So let's go back to the muon. So we have this muon that's zipping down towards the Earth from the Earth's point of view. So Earth's point of view. Muon's heading towards it. We claimed it went 1,977 meters, and the amount of time it took was 6.3 microseconds, something like that. Or, what was the number again?
It's written on the board.
Still there?
For the
Oh, there we go, 6.3 microseconds, or 6.4. From the muon's point of view, the Earth, so point on view, the Earth was coming towards it at the same speed, so this was at beta is equal to 0.9952, and this would be beta is equal to 0.9952. Again, they agree on the speed, they just disagree what's moving that fast. And the time it took was 0.625 microseconds. So they disagree on the amount of time that took place, and they disagree on what's moving. What about the distance?
They should have gone the distance also,
That the distance would be the same or different?
the same,
Why?
no information.
Okay. Let's think about it. What is, so I know that, speed is distance over time. By definition. So the distance traveled should be speed times time. So they agree on the speed, they disagree on the time. So what does that mean about the distances?
It's gonna be different. It's gonna be different.
By the same factor. So we have that time is equal to gamma times the proper time. However, the proper distance, remember, the proper value is the one measured when you are at rest. Well, the top of the mountain is at rest relative to the earth. So the formula looks like they switched something around. All they did was just shift what the proper length was. So proper length is equal to gamma times t. This is still the earth side in our example, and this is still the muon side. But officially, proper length was from the earth's point of view. Proper time is from the muon's point of view. The first one is known as time dilation, as was written before.
Wait, is length the same time as distance?
Yeah, I mean, the distance that it travels was the height. Yeah, like in this particular case. And this is known as length contraction. So if you can zip up near the speed of light, so let's keep it, pseudo-realistic. You get near the speed of light, not only do you not age as fast as everyone left behind, but the distances are shorter. So if length contraction is true, how fast does an 11-foot car need to travel to fit into a 10-foot garage? In other words, the entire car will be inside the garage in 1 moment. Well, when you're given a problem like this, you got two numbers here. The trick is to figure out what gamma is. What is the ratio that's going to cause this shrinking? So I have car. Sure, car looks like that. 11 feet. I have a barn. Or a garage. I will probably keep calling it a barn, because there's another problem that we're going to do where it is a barn. It's a pole and a barn. And for whatever reason, my brain just keeps calling the garage a barn. So I have a car going to fit into it. This is going to be from the garage's point of view. From the garage's point of view, the size of the car is shrinking. From the car's point of view, the garage is shrinking and it won't fit all inside at the same time. So I have two numbers here and I want to figure out gamma. So what's the smallest value that gamma can be? We plugged in various values of beta, and gamma seemed to do something, so what's the smallest?
0.1.
What would be the value of beta to get 0.1?
Or 0.1 is beta. That's the smallest one we did for beta.
Okay, but if beta is even smaller, what's the limit? the lower limit of gamma.
Oh, the 1.005, that's what, when beta is 0.1.
All right, and if beta is smaller,
Oh, yeah, beta is like 0.9952, gamma is 10.21.
okay, so if we make beta smaller, what's the smallest beta can be? Yeah, so when beta is 0, what is gamma?
Infinite.
No, when beta is 0. When beta is 1, gamma is infinite. When beta is 0, 1. I'll have to reset it. So gamma is 1 over the square root of 1 minus beta squared. If beta is 0, I get gamma is equal to 1 over the square root of 1, which is 1. So I have two numbers here. I know that the ratio, whether it's, that should be L there, not T. Hopefully you wrote it down correctly in your notes. LP equals gamma L. I have two lengths. I know gamma cannot be smaller than 1. So gamma is the only other ratio I've had with these two. So whichever one's 11, whichever one's 10, I know gamma's got to be bigger than 1. And so this would be gamma is 11/10 or 1.1. But the question is, how fast does the car need to travel? So I got a formula for gamma, and I set it equal to 1.1. So 1.1 is equal to 1 over the square root of 1 minus beta squared. So the square root of 1 minus beta squared is equal to 1 over 1.1. 1 minus beta squared is equal to 1 over 1.1 squared. 1 minus 1 over 1.1 squared equals beta squared. So beta square root of 1 minus.
Zero point 416.
Okay. So about 41.6% of the speed of light, and you can fit this 11-foot car into the garage. In other words, in theory, it's a thought experiment, since we can't get something that massive that fast. In theory, it could get inside, if we had open ends on both of it, the car could come in and immediately close the doors. Think Star Wars Death Star doors when they do go, except faster. At which point the car is going to crash into the back wall. Or is it? So we'll get into that. So if your mind is still working well with this and you're going, yeah, okay, this all makes sense. Let's change that. Questions before I do another thing that potentially messes with your ideas of reality? All right, let's mess with some reality. Another thought experiment. I got a track right here. I got a train car. And I have a detector in the middle of the car. A lot of the problems deal with Sue and Lou on the test problems, but before Sue and Lou, there was Peggy and Ryan. So I got Peggy. Now Peggy's on top of the train just because that's the way I drew it, but there's no reason she has to be on top of the train. She is smack dab in the middle of the middle of the train, so equidistant from both sides, and the detector is smack dab in the middle, perfectly in the middle. Over here, I have a light waiting to go off. I have two flash pots or something to do things that are gonna flash light in a moment. On the side over here, there is Ryan. Now, when the detector is at its closest distance to Ryan, in other words, the line that intersects Ryan and the detector makes a 90-degree angle with the track. At that point, these two lights are going to go off. Ryan is going to see them flash at the exact same time. He confirms it because he has his own detector down here, and he sees that the light reaches the detector at the exact same time. Meanwhile, inside this detector right here has a special thing, that if we'll call this the right light and the left light. And if you're not quite sure why I came up with those names, just talk to me afterwards, I'll be glad to explain. If the right light gets there first, gets to detector first, the detector glows green. If the left gets there first, or it's a tie, gets to detector first, or right and left at the same time, the detector glows red. Obviously, there's going to be disagreement about what the detector will glow afterwards. So here's the logic. Ryan on the side here sees the two lights go off at the same time, and he's confirmed that the lights went off at the exact same time. Lights go off at the exact same time, and then Ryan goes, well, then the cart is moving to the right. When the light is released from it, the light takes time. So we have light from the right coming this way, light from the left coming this way, but the detector is moving towards the right side. And therefore, the right light will get to the detector first if the detector is moving. And so Ryan says, the detector will glow green. Peggy is sitting there and she's going, wait a second, those lights are going off at the exact same time. They're at rest relative to me and the detector. Therefore, if those lights go off at the same time, the light should get to the detector at the exact same time. So Peggy's prediction, it'll glow red. So they run this experiment, they stop the car, and they look at the detector, and the detector glows green. What is wrong with Peggy's logic?
Nothing.
Okay. Then what is wrong with the assumption she made? The way I worded it, actually, there was nothing wrong with what I said, but there was a built-in assumption which was wrong.
That the detector wasn't moving.
Well, it's not, I mean, the detector, relative to Peggy, the detector's not moving. And neither are the two flash, the two things giving off the flash. They are all at rest relative to each other.
But what about the other detector?
Oh, that Ryan had?
Yeah.
Yeah, that doesn't affect this. That's just confirmation that Ryan says, yeah, those lights went off at the exact same time.
How does Peggy know they went off at the same time?
Pardon?
How does Peggy know they went off at the same time?
She's been working with Ryan for years. However, you want to explore that a little bit further?
Because you can't physically look at both of them at the same time. At her point.
Well, but she does have a detector here. I mean, what's wrong with, I mean, the thing does, the right light gets there first. But both of these are at rest relative to Peggy. The detector's at rest relative to Peggy. There's something that must be true in order for that thing to be glowing green.
The ground is moving relative to the bank.
Yeah, but the ground's not going to affect Peggy's assertions. Or Peggy's line of reasoning.
Peggy also at rest?
Relative to the lights. I mean, she's at rest relative to the train car, relative to the lights, and relative to the detector. Kyle came really close to nailing it.
What did Kyle say again?
She's on the top of it, so,
She is sitting on top.
I forget what I said exactly, but like I said,
Was it that she couldn't see both lights at the same time? Is that what you were saying, referring to?
No, there's something else you asked. The question he asked was, she doesn't know they went off at the same time.
yeah, that's.
And then I talked about the fact she and Ryan have been working together for a long time, and she trusted Ryan. All right, suppose you're at rest. Suppose I'm smack dab in the middle of the room. I got my detector right here. I got lights on both sides. And if it's a tie, it'll glow red. If that one gets there first, it'll glow green. If it glows green, what must be true? Assuming the equipment works. The walls are at rest relative to me, detector's at rest. I'm Peggy in this scenario,
So one of the lights is traveling faster?
but they're gonna travel at the same speed.
They had, travel in the same direction.
They're traveling in opposite directions, but heading both towards the detector,
You travel different distances?
same distance,
Different time.
same time. Well, they travel for the same amount of time. It's interesting, there's that leap that people need to make in order to see it. All right, ignore the train car for just a second. Ignore that. We got an experiment set up.